Hello students, in this video we'll use Abel's test to prove that particular Fourier sine series converges for all real values of x. Let's show that this function, let's call this function g of x, which is the sum, k goes from 1 to infinity, of the sine of kx over k, converges for all x in R. Converges for all x. I'm just going to say between 0 and 2 pi because this function is 2 pi periodic, clearly, okay? Each of these summands is 2 pi periodic. Now, of course, if I plug in either 0 or 2 pi, I'm going to get g of those values are identically 0. So note that g of 0 is equal to g of 2 pi is equal to 0. So I'm going to fix an x that's not equal to either of those values. So I'm going to fix an x, so fix x in the interval, open interval 0 to 2 pi, okay? And so let's recall Abel's theorem. So what's Abel's test say? So Abel's test says that if you have a series like this, the sum k goes from 1 to infinity of ak, bk will converge if the partial sums of ak, of the ak sequence, are bounded and the bk are decreasing. So if bk are decreasing and the partial sums of the ak are bounded, then the series is going to converge, right? So over here we have a good candidate for the bk. So our bk in our problem is just going to be 1 over k, and that's clearly a decreasing sequence, so that's good. So all you need to do is show the partial sums of this other series over here, the sine of kx, are bounded. Okay, so let's do that. So to do that, we need to show that the sum k goes from 1 up to n of the sine of kx, those are the partial sums of the other terms, are bounded. Okay, for a fixed x, okay? So I don't need to show uniform bound, that's something different. I just need to show for a fixed x that they're bounded, okay? So let's do this. So here's the trick. We're going to call this function over here. I'm going to call this function over here. What should we call it? Let's call it function over here h of x. It's a modification of the Dirichlet kernel, right? So this is sort of a modified Dirichlet kernel. It's missing one term in the Dirichlet kernel. So what I'm going to do is, here's the trick. So the trick is to multiply h of x by sine of x over 2. And so why am I going to do that? Well, then this becomes what? This becomes the sum, k goes from 1 up to n, of the sine of what? And I'll help with the 2, well, it doesn't really matter so much. Sine of x over 2, and then a sine of kx, like that. And just to make my life a little bit easier, I'm going to put a 2 over here and a 2 over here. Because why? Because I know a formula for the sine of twice a times b, right? So I know that the 2 times the sine of alpha times the sine of beta, well, both those terms occur in the difference for cosine, right? So that's going to be a cosine of alpha minus beta. Cosine of alpha minus beta is going to be cosine alpha cosine beta times plus sine alpha sine beta. That's one of them. And then if I do the minus cosine alpha plus beta, then what will happen over there? Then that's going to have a minus sine alpha sine beta. So this is a product to sum identity over here. So now I can use this product to sum identity to say that the sum over here is nothing more than just the sum. K goes from 1 up to n of what? Of the cosine of what? Well, I have to add these things together. The first thing I have to do is subtract them. So I'm going to let my alpha over here, I'm going to let my alpha be this thing over here, the kx, and then my beta over here be the 1/2, right? So this is going to be k minus 1/2 x, like so. Good, that's my alpha minus beta. And then what? And then minus a cosine of k plus 1/2 times x. That's beautiful because it's not the telescopic sum, right? So of course, the first thing I'm going to get is I'm going to get a cosine of 1/2, cosine of x over 2. And then the last term of this, I'm going to get minus cosine of n plus 1/2 x. Okay? Great. So we've just proven the following formula. We've just proven that h of x, our function h of x, is really going to be the cosine of x over 2. Of course, this h of x depends, let's call this hx of n. It depends on n over here, right? So that's hn of x. So these are n's, right? Cosine of x over 2 minus cosine of n plus 1/2 x, all divided by 2 times the sine of x over 2. Okay? Good? And so now, of course, the numerator in absolute value can be no larger than 2, right? So I can say that this thing over here, this implies that the absolute value of hn of x is less than or equal to 1 over 2 times the sine of x over 2. Okay? And of course, what's the real danger over here? So now when x is between 0 and 2 pi, that says that x over 2 is between 0 and pi. So let's look at the graph of sine. So the graph of sine looks like this, right? Looks like that. And there's 2 pi. There's sine. Now that's the graph of sine of x, right? There's x, there's sine of x. Okay? So since I'm not at 0 or 2 pi, this is bounded, right? This is just some number over here. So the partial sums of these hk's in my series are bounded. So we've just shown that the partial sums of these things are bounded for a fixed x. So when x is fixed, this is just some number, right? This is less than infinity for just some number, right? For x fixed. So in particular, it shows for a fixed value of x, this series is going to converge. So therefore, this series g of x converges for all x in the interval 0 to 2 pi. And so we have our Fourier Sine series over here defined in this way, converging for all real values of x. So Abel's test is a very powerful tool when you're dealing with Fourier series because we have these bounds on these so-called Dirichlet kernels or modified Dirichlet kernels away from points where it's zeroed out in the denominator. Thank you very much.